Today we're going to be talking about embeddings. Many people know what embeddings and language models are, but they want to understand more of the details. I'm hoping to open up that path for you by showing you some examples and clarifying underlying concepts. So sit back and enjoy. In machines, similar concepts are mapped to similar regions of space. What we're talking about when we say embeddings is the activations inside a neural network when a particular input is passed in. If you were to pass in two different inputs, the internal activations would be different. And it's exactly these differences that allow the neural network to achieve downstream tasks, like classifying cats and dogs. I want to jump to my personal favorite example of embeddings, which emerged in 2013. It's 2013 and a team of researchers at Google released a series of works. They took a new spin on language modeling, which they called word-to-vec. In a very Google fashion, the team scaled up their language model to very large data sets and learning to make the data do the work for them. In word-to-vec, two different approaches were explored. Today, we're going to look at the skip-gram model. The idea is very simple. Use the current word in a sentence to predict words that occurred before and after it. At first, predictions will be very poor, essentially random. But with the appropriate learning schema, we can get better and better at making predictions. We can write down this objective mathematically as follows. For each word T in a sentence, we want to increase the probability of predicting its neighboring words. We can define the neighborhood any way that we want, but a common choice at the time was 5 words before and 5 words after the current word. In order to optimize this objective, we have to come up with a language model, which will provide us with the probabilities, given the context. Let's get started. From a given sentence, we have the current word T and a neighboring word N. The first thing we'll do is map each of these to a unique vector. At first, these vectors will be random. However, through learning, they will become more and more aligned to improve predictions. Given the vector for the current word and the vector for the neighboring word, we can then compute a similarity score. The higher the similarity, the higher the probability that the neighboring word will be predicted by our language model. As for this embedding step, you can think of it as looking up a word in a table. For example, in this table, the embedding for the word candy is the first row of numbers. Word2Vec actually uses two different embedding tables, one for inputs and one for the predicted output. Therefore, each word in the vocabulary has both an input embedding and an output embedding. When the learning procedure is finished, either of these tables would be appropriate to use as your embeddings. And to distinguish these, we're going to denote output vectors with a Z and input vectors with a V. As for the similarity between the input and the output vector, we can simply use the dot product. When the two vectors mostly point in the same direction, their dot product will be high. If their components point mostly in the opposite direction, their dot product will be negative. And if their components are mostly unrelated, randomly agreeing and disagreeing, then the dot product will be approximately 0. Okay, so far we're saying that the probability that the current word T is surrounded by a neighboring word N relates to how similar their vectors are. For various reasons, we're going to take the exponential. One reason is that the dot product between vectors can range from negative infinity to positive infinity, whereas the exponential will always be positive. So this gets us closer to probabilities. Moreover, we don't want our vectors to blow up during training. With this exponential, two words can be exponentially attracted or repelled due to a simple linear change in their vectors. And in turn, this means our learning algorithm will be more stable. The vectors will have a much more reasonable scale by the end of the learning process. We're not quite done yet. Right now, we've come up with a compatibility between the current word T and its actual neighbor N. But there's also the compatibility between the current word T and any other word, such as the first word in the vocabulary or the second word in the vocabulary, and so on. How do we know that the actual neighbor is more compatible? So finally, to account for competing possibilities, we will divide by the sum over all possible words. This gives us a normalized probability distribution. Let's visualize this. As you can see, we're really modeling the distribution of plausible neighbors. You could imagine two sentences start the same way, but differ by their last word. Multiple last words could be valid. Depending on the particular sentence, sometimes the model will be right, sometimes it will be wrong. But on average, across many sentences, it will do as good of a job as it can, given the inherent uncertainty of the task. Recapping, the probability that the neighboring word is some word is the score for that word divided by the sum of all scores. This operation is called the Softmax, which you might have seen before. Let's now fill in our objective using our language model. For each word T in a sentence, we want to increase the probability of predicting its neighboring words, and now we have a description of that probability based on word similarities and the Softmax. There's just one problem with the Softmax. Comparing scores across all possible words in our vocabulary is quite expensive, and we're going to want to do this over and over for each sentence, for each neighbor. Now, to be fair, these days, this wouldn't even be a discussion. Large language models simply use the full Softmax. But at the time, in 2013, there was a lot less compute, especially for researchers just playing around with words. So even though this proposed language model for Word2Vec would be very powerful if it was trained to completion, it simply couldn't scale at the time. So what did the team at Google do? They threw out the Softmax and tried to optimize for something else. At the heart of their method, they tried to think about what scores should go up and what scores should go down. Well, we definitely know that we want the dot product between the input word and the target word to go up when we perform an update to our language model. But how about all the other words? The main insight the team had is that a randomly sampled word from our vocabulary is most likely unrelated to the current word. Therefore, we can treat a randomly sampled word as a negative example. So they converted the task into a classification problem with only two options, real or fake. The new objective would push random words away from the current word while attracting real neighbors. And we could actually visualize this as shaping the network of words so that similar words group together and unrelated words repel. By the way, there's actually a follow-up algorithm called node2vec that learns to embed nodes on a graph in this way. Okay, so let's walk through the training procedure. At each training step, we'll get a batch of words from a sentence. Starting with the first word in the sentence, we'll gather its neighbors. Then we'll add in some randomly sampled words. All of these words will then be looked up in the embedding tables. The input word uses the input embedding table, and all other words are mapped to their output embeddings. The combination of real and fake pairs will create a balanced gradient, which we'll then optimize against over and over across the sentences in our dataset. To achieve the right balance, a hyperparameter to tune is the number of fake words that we'll mix in, which are often just called negative samples. We would repeat a very similar process for all the other words in the sentence. In our full training pipeline, we would sample several sentences with real and randomly sampled pairs pre-computed using a data pipeline. TensorFlow actually has an amazing tutorial on implementing Word2Vec from scratch, which I recommend for anyone who wants to dig in. So here's how Word2Vec actually models these probabilities. According to our model, the probability that a word N is a real neighbor for the current word T is the sigmoid of their similarity. This looks really complex, so let's talk it through. The sigmoid is used for binary classification. If the dot product between the current word and the neighboring word is high, then the probability that they're a real pair approaches 1, which makes sense. And if their dot product is low, then the probability that they're a real pair approaches 0. I do want to spend a moment looking at this magical sigmoid function. It shows up in a lot of places, like logistic regression for binary classification, or ELO ranking systems for video games. As the inputs to the sigmoid become large, the sigmoid approaches 1. Likewise, when the inputs become very negative, the sigmoid approaches 0. Another really nice thing about the sigmoid is that its complement has a really simple form. And when used to model binary probabilities, everything fits together very neatly. The sigmoid is basically the yes-no version of the Softmax, making this binary choice is computationally much simpler. So returning back to our model, this is how we'd write down the probabilities for fake cases. The probability that a random word is a fake neighbor, according to our model, is 1 minus the probability that it's a real neighbor. And if we use the property we just learned, we get a really nice formula. If the dot product between the current word and the fake word gets smaller, then the probability that they are a fake pair will go up. Altogether, we've derived what is called the negative sampling objective. We've come a long way from trying to predict probabilities of surrounding words to distinguishing between real and fake pairs. And by performing gradient ascent on this objective, the embeddings will align in a meaningful way. This objective is highly scalable. The number of fake examples k mixed in per real example is much smaller than checking every possible pair. Only a few number of negative samples are needed to get high-quality embeddings. What we're looking at here is an interactive tool developed by TensorFlow, which lets us explore the embedding space. The words we're seeing highlighted are nearest neighbors, although we're projecting to 3D, so it's a bit crowded. I recommend you try this tool out at home. It supports any type of embeddings you upload to it. Another incredible property of word-to-vec embeddings is that you can meaningfully perform vector operations on them, like adding and subtracting concepts. The ML world exploded with excitement when they saw this, and I don't think this picture will ever get old. How about another example? Embeddings can also help machines translate from one medium to another. CLIP is trained by aligning text embeddings and image embeddings. In this diagram, CLIP's goal is to produce similar embeddings for this puppy, whether it gets an image of it or gets a text description. We now have the tools to talk about what's going on here. In word2vec, the current word was matched with a real neighbor and was simultaneously repelled from random words. In CLIP, the exact same type of contrastive learning is going on. An image and its text caption are a real pair. Meanwhile, an image and text captions for other random images are fake pairs. And if you have a batch of n captioned images, this can all be nicely organized into a matrix. The blue pairs along the diagonal are real text-image pairs, and the gray are fake. The same principles apply. In this case, the text encoder and image encoder are deep neural networks instead of lookup tables. But as we can see, their objective tells the same story. Once CLIP learns how to align language and imagery, it can be used to do all types of amazing things, such as automatically captioning images. Rewinding back to our timeline, let's talk a little bit about what changed because of word2vec. Word2vec was a significant simplification compared to other architectures of the time, and due to its scalability, it was trained with bigger sized vectors on an unmatched amount of data. Moreover, it scaled so well that it was possible to test a bunch of different tricks and hyperparameters, which is really critical to the success of any ML method. In my opinion, word2vec is one of the most compelling examples of its time, where a much simpler algorithm combined with a massive scale-up led to unparalleled results. It is also part of the trend of training on a huge dump of internet data without any labels. Let's emphasize that. One benefit of the learning algorithm is that you don't need labeled data. You just need to grab some sentences in the wild. Then, all you do is learn how to predict which words are surrounded by other words. We call these types of methods self-supervised, since the data labels itself. Large language models of today still ride off of this principle. Their objective is simply to predict the next token that appears on some part of the internet. And it turns out that predicting which word will come next is a very general task. Instead of being fixated on one task, such as sentiment analysis, we expect language models to be able to do anything that can be written down as language. This includes things like proofreading, translating, and even coding. While it is true that some predictions will be easy, like the sky is blue, it's the complex ones that continue to drive learning. And as we can see here, the loss has not yet stagnated. There's a fantastic talk by Ilya Sutskever, the chief scientist at OpenAI. His team compared the quality of embeddings obtained from different learning objectives. Their research showed that models trained to predict the contents of an image pixel by pixel have incredible quality embeddings, and yet these embeddings were obtained in an entirely self-supervised fashion without any labeled data. Pixel by pixel predictions are the image analog of token by token language modeling. They're both called autoregressive models. It's precisely this learning objective that the world continues to take to the limit. So different tasks have different properties. It makes sense that depending on what outputs need to be predicted, the internal representations of a model will align accordingly. Perhaps this classifier is really good at identifying cartoon robots. The downside is that embeddings for this model might not be very helpful for an unrelated or novel computer vision task. On the other hand, if you have a very general model, its embeddings would be very useful for downstream tasks. For example, it's common practice to swap out the last layer of a large language model and train a light classifier on top of its existing representations. You can actually try this out on Hugging Face. In deep neural networks, the different layers provide different types of representations. In computer vision, later layers often capture higher and higher levels of abstraction. We're going to demonstrate this with one final example, style transfer. This method works by extracting features from different layers of a pre-trained convolutional neural network. First, we'll pass in a painting and extract stylistic features from the activations of each layer of the convolutional neural network. Earlier layers capture local blips of style, while later layers capture more global strokes. Next, we'll capture content-based features from a photo. In this case, earlier layers are highly precise and capture exact shapes and positions. What the authors discovered is that you could create a brand new image that is optimized to have the style of one image and the content of another. The arrows here represent aligning of embeddings across the various images. Now let's actually look at the process of synthesizing an image. What you're seeing here is gradient descent being performed not on a model, but on an image itself. Starting from noise, the optimization objective is to align the embeddings of this image with the style from one and the content from another. It's simply incredible. And that's it. We've built up a map of embeddings, where they come from, how we can optimize them, and why they matter. There's so much more to say about embeddings and also how they can be applied in various settings. For instance, social media companies use embeddings to understand users, to serve them better content. E-commerce companies use embeddings to recommend products that fit well together. YouTube and Spotify allow you to search over videos and music, all powered by embeddings. I hope this was a good introduction for you, and I plan to break it down in future videos. Thanks for listening, and I hope you enjoyed.